Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last few classes we have been discussing about finite volume approach, and we saw that how it is different from the finite difference approach. We saw that we use the integral form of equations, and we have to basically find the residual, and we can use our own time marching scheme for after we find the residual. So, we convert the PD to an ODE by considering that the cell centered values is the average of the value within the cell. Okay. So, what happens is basically if you have an expression du by dt, okay, plus df by dx equal to 0. Okay. So, this becomes du by dt is equal to f let us say I plus half minus f I minus half minus. Okay. So, this is nothing but your residual. Okay. Maybe you can write delta x here. Okay. So, once you calculate the residual, you can employ your own favorite time marching scheme here and solve the problem. Okay. So, we have discussed the nuances of finite volume scheme, how to get the value of f I plus half and f I minus half. So, you will have cell center on left and right. How do you go from this, let us say this is I and this is I plus 1. So, this will be I plus half. So, how do you basically get the value from left and from right, which one you should choose? Okay. And if you choose both of them, then how do you get the value, the unique value here, right? So, that is where the flux schemes comes in, whether you use the Lax-Frederick scheme or the Roy scheme or von Leer scheme or any scheme HLLC, AUSM. So, what they do that they will take the reconstructed values from the left and right across any cell and give you the unique flux. Okay. And there are certain properties on how the flux should be, so that the code does not diverge, and these schemes basically retain those properties. Okay. Good flux scheme basically retain those properties. Of course, while trying to do that, you may also have some dissipation in the scheme. Okay. So, this is similar to what we have discussed in finite difference. We had several different schemes, okay, and we discussed about the stability and the accuracy of different schemes. What we will do today is we will basically try to implement whatever understanding we have in finite volume for 1D problems, and of course, the 2D and 3D problems are extension of those 1D problems. Okay. So, let us start. So, we will start with the convection diffusion problem, because this is what we have been doing when we started the finite difference. Okay. So, the equation that we are trying to solve is basically del u by del t is equal to r plus c del u by del x is equal to nu del 2 u by del x square, right. This is the convection divergence equation, and this is the viscosity term. Okay. It can be, let us say, if you are solving a thermal problem, this can become thermal conductivity, and if you want to solve it, let us say in finite difference. Okay. So, you will make a grid. Okay. This is I plus 1, I minus 1, and let us say you want to write the solution here. Okay. You can just use this, let me call this O. Okay. And this I minus 1 is left of this, so I will call this left, and I plus 1 is the right of this will call right. Okay. The same. So, without looking at the cell center here or the cells here, you can just write the finite difference scheme, which is basically, let us say del u I by del t, because we are doing at I is equal to minus c u I plus 1 minus u I minus 1 by 2 delta x. Let us say if you are using central differencing for center, and so I am just assuming that we are using central differencing, but we have discussed that there are some issues with the central differencing. What I intend to show you today is that, let us say instead of finite difference you use finite volume in 1D. So, what are the differences that you see, or is there any difference? So, we have taken a uniform grid as of now. Okay. So, this will be u I plus 1 minus 2 u I and plus u I minus 1 by delta x square, right. This is what we have studied many times. Okay. So, you can write it in terms of L, O and R, this is how it will become, right. So, this is your expression if you want to solve it using finite difference. Okay, but what we want to do is we want to solve using finite volume. So, what we will do, we will make grid around it. Okay. So, there will be a grid here, okay, there will be a grid here and there will be a grid here, right. So, this is what we call as I plus half, okay, this one is I plus half, this is I minus half, okay, and this is basically I minus 1 minus half, this is I minus 3 half, I plus 3 half and so on and so forth, right. Because we are using in finite volume, so how we will represent it for the general convention, we will call this as small r and call this small l on the left. Okay. So, you can see it here. So, the left cell, the cell center is denoted as a capital L, capital O and capital R, and in between you have basically the between the center cell O and the left cell L, we have an face, okay, which we call as denoted as L, small l. Okay. Similarly, between O and R we have a face. So, these are the faces, okay, these two are faces for cell O. Okay. So, we need to basically find out values at L and R. Okay, we will use very simple scheme, take the average between left and right and do that, and let us try to solve using the finite volume. So, when you are going from finite difference to finite volume, this was your finite difference. When you go to finite volume, so what you need to do is basically you need to integrate it, right. So, this will become u t is equal to minus c u x nu u x x, okay, and basically integrate it because we are looking for the solution in O. So, I will integrate it from left to right, right, or in other words I minus half to I plus half. Okay. So, this is basically I minus half u t to I plus half is equal to minus c u x and nu u x x I minus half to I plus half. Okay. Now, in 1D I minus half and I plus half is very convenient, but when you go to 2D or 3D, what will be convenient for you is the left and right. Okay. So, let us say if you have a 2D flow and your grid is something like this. Okay. So, you can see that, okay, let us select one particular cell, this is my cell, and depending on the direction how you what is your convention. Okay. So, let us say I am doing this way. Okay. So, if you are going along this, so this is my for this edge, this is my left cell, this is my right cell, and for this edge, okay, it is the same thing, this is left cell, this is right cell. For this edge, this is my left and this is my right, right. So, for every given cell, for any given cell, okay, you can find. So, this is your cell here and it has got 3 edges here. Okay. So, you can find out along every edge or along every face what are the left cell and the right cells. Okay. So, for this edge there will be left and right cell, for this cell there will be left and right cell, for this edge there will be left and right cell, and for this one also left and right cell, right. So, that is why this left and L and R conventions are very convenient. So, if you take this edge here, this one, okay, this is my left and there is one on the right. Okay. Now, there are two kind of conventions used in finite volume. One is that you know that we have this local conservation in every single cell, right. So, what you can do, go for each cell, let us say let me call this cell as cell I. Okay. So, for cell I, okay, loop over all faces, okay, basically phase 1, phase 2, phase 3. Okay. So, loop over all faces and calculate the integrals and then sum that up and finally calculate the final residual, okay, which is the summation of the residuals and all the 3 phases, right. The other approach that we use in finite volume is basically looping over faces. So, this was looping over cells. Okay. So, what we are doing, we go to each cell one by one and then look for the faces of that cell. So, right now it is a triangular, but you can have a quadrilateral face also. If you go to 3D, you can have the hexahedral, it can be prism, it can be pyramids, you can have 3 faces in certain cell, 4 faces in certain cell, 5 faces in certain cell. So, that you need to see. So, basically you have to go towards each cell, find out the residue in each cell and sum it up, like we have been doing, right, delta sigma f perpendicular j delta s j, right, and this you have to do in every single line. So, the first approach is loop over cell, go through each cell and look for the faces and add that up. The other is loop over cells, loop over faces. Okay. So, what will you do in this case, that you know how many number of faces you have. So, for I equal to, let us say 1 to number of faces. Okay. For every face you will have a left cell and the right cell, right. So, calculate the residue, okay, and you add the residue on the left cell, okay, residue L is equal to residue L plus the residue nu, whatever let me call it, which is the integral, and subtract from the right cell. How are we doing it? So, it will also basically, if you keep on adding all these things across all the faces, ultimately you will see the local conservations in every single cell. So, how it is working, if I can explain you here. Okay. So, you recall, so this is my I plus half and I minus half. Okay. This is my right cell and this is my left cell, right. So, f perpendicular j delta s j, if you do that. Okay. So, here this is normal, this normal is positive 1 0 0 and this is for this particular cell I, this is, so because the normal always points out on this direction. Okay. So, this will be minus 1 0 0, right, and then if you add that up. So, basically this is f I plus half minus f I minus half, right. This is for particular cell I. So, this is the looping over cells. So, this is looping over cells, okay, and I representation, and you will be basically looping over all the cells from I equal to 1 to I equal to n. Okay. If you do a loop over faces, okay, so then what will happen is basically you, let us say you go to this face, okay, and then you have another cell on the right which is I plus 1. Okay. So, let us say I am looping over this particular face. So, for I equal to 1 to n f, okay, number of faces. Okay. On this face what will happen? This will add to the left. So, for this particular face, okay, this is adding to the left and subtracting from the right, right. So, what you can say that, okay, if I am looping over faces, so my residue in f I will be residue in f I plus f j plus half, I plus half, right. And similarly, if you go to residue of I plus 1, so this will become residue of f I plus 1 minus f I minus half, right. Similarly, if you go to this one, this particular cell which is the left of I cell, okay, so this is become negative for the I cell and positive for the left cell of this, right. So, everywhere you are seeing that if you are following a direction, so it is basically adding to the left cell and subtracting from the right cell. Okay. So, that the same philosophy works here also in the 2D flow, that you can basically loop over faces and keep on adding, calculate the residue, keep on adding on the left cell and subtract from the right cell. If you do that, you will be basically ensuring that all the contributions due to all faces in the cell has been taken care, right. So, this normally this approach is followed more, where you basically loop over faces. Okay. Now, this was a slightly detour, but let us say that we want to solve this convection diffusion problem using our finite volume approach. So, this is how it will look like. Now, it has got two terms. Okay. So, we are integrating from left to right. So, we are basically interested in this particular cell, okay, and we are integrating from left to right. Okay. So, this is an approach which is loop over cells. Okay. So, we have a convection term and then we have a diffusion term, okay, and we call this this term as A advection term, this term as D. Okay. Now, let us calculate the advection term. Okay. So, advection term is minus of like C u x dx, okay, where or if I may write A equal to minus L to R C del u x divided del x dx, right, and if you integrate it, okay, L to R basically C u, okay, yeah. So, then it will become C u r minus u l. I think there will be a negative sign here. No, this is left to right, this is correct. Okay. So, now what you will do, look at your diagram, what diagram we had, this is O, this is my R, this is R, this is L, this is L, right. So, if we want to calculate the value at R, so u r, so here let me write here, this is u r will basically I am just taking the average of O plus R. Okay. So, I am just doing the zeroth order reconstruction. So, we are saying that whatever value we have at the cell center, the same value is available at the face also. So, u r will be basically u o plus u r by 2. Okay. Then u l will become basically u l plus u o by 2, right. Substitute these values here, okay, and then you will find A will be minus C u r minus u l, then minus C u r is nothing but u 0 plus u r by 2 minus u l is u l plus u 0 by 2 or u o by 2. This will get cancelled out. This will become minus C u r minus u l by 2, right. So, we got the advection term. Now, let us look at the diffusion term. Okay. So, as we have been discussing that if you go to a diffusion term or the viscous term in a general terminology, so you have to have the gradient also available at the faces, right. So, you can integrate it and finally, you will have the diffusion term which is basically nu del u by del x r minus del u by del x L. Okay. Now, use a very simple central differencing approach here. Okay. So, diagram is here O R L, this is R, this is L. So, we want to calculate del u by del x at R, right. So, this will become u r minus u o, okay, minus 2 into delta x by 2. Okay. I am assuming uniform grid size. So, this is my delta x, right. So, this will become okay. So, yeah, I think this is become like this only. So, that will become u r minus u o by delta x. Okay. And similarly, if you go to du by dx at L, so that will become u o minus u L by delta x, right. So, this distance is delta x. Okay. So, so we have these two values. So, finally, your d will become, you can use substitute this value nu del u by del x r is u r minus u o by delta x and minus u o minus u L by delta x. Okay. So, that will become nu u r minus 2 u o plus u L by delta x square. Okay. So, we got the value of the diffusion and we got the value of the advection earlier here, okay, which is here. Okay. So, if you combine these two, okay, right, see here. So, you are combine these two and then we are saying that okay, I am using a cell average value. So, basically whatever value you have u 0, it is basically average of u into the dx, okay, and then 1 by delta x, right. So, if you use this relation, then your you can basically take the del by del t out, and this become del u naught by dt and delta x and minus c u r minus u l by 2 and plus this is what we got, and finally, if you arrange it properly, it will become like this, right. You can see and you can go back and compare this with the finite difference expression. Okay. So, the finite difference expression also gives you the same thing, right. So, if the grid is uniform one dimensional, then the finite difference and finite volume basically result same thing, okay, for 1D uniform grid. Okay. So, in finite difference we just use the discretized scheme on a differential equation. In the finite volume we integrated those equations, okay, and then we used appropriate basically definition for getting the value at the face and the gradient at the face, okay, and we found out that both gives you the same thing. Okay. Of course, when you want to code it, it can you can code it in a different way. Okay. You can calculate the residue on each side, each face, add it to the cell, and then finally you can in time integrate it. Okay. So, here you can use whatever time integration scheme that you want. Okay. You can use the Euler forward or Euler backward or maybe the Runge-Kutta or multi-step time stepping, anything that you know. So, let us stop here and we will start a new topic from the next class. Thank you very much.